If you would recall, we are looking at second order differential equations, specifically second order ordinary linear homogeneous with constant coefficients, the simplest of the second order equations. The technique that we used was our favorite technique to solve problems in math class, and that is we guess. We observe that y double prime, y prime, and y all have to be like terms. And so the only function that we could think of whose derivatives are like terms, e to the kt, because the derivative of e to the kt is k e to the kt. All we pick up is a constant. When we put y prime and y double prime back into our original equation, we were able to factor out the e to the kt part because that's never equal to 0, and we're left with a quadratic equation called the characteristic polynomial. This will give us two values of k, and that'll be solutions. So then we'll have two solutions to our second order equation. Since we're dealing with polynomials, we have to think about what could happen when we're solving polynomial equations. A quadratic equation could have distinct real solutions, a repeated real solution, or complex conjugate solutions. I said solutions because I said equation. I wrote roots because I wrote characteristic polynomial. Trying to be consistent with the language, but I'm not consistent with what I'm referring to over here. The important thing to recognize here is that we're going to end up with two different solutions. And we got to think about how to combine them into a general solution. So let's take a look at an example. So he'll have -4 and +1, that's -3. So we make our guess, y equals e to the kt. We take two derivatives, we plug it back in, we know what's going to happen. We're going to have an e to the kt times k squared minus 3k minus 4. So our characteristic polynomial will be k squared minus 3k minus 4 equals 0. And so that tells us that k equals 4 and -1. We skip the part where we write down what our guess is, plug it in, and find the characteristic polynomial. We know what's going to happen. The point of being in a math class is not have to do all the math all the time. We know what's going to happen. It's going to be k squared minus 3k minus 4. This is factorable because I'm lazy. It's going to be a k plus 1 and a k minus 4. So our solution will be -1 and +4. So this tells us there are two possible solutions. Just like with the exponential, excuse me, our two solutions, we can put a constant in front of them, just like we did with the exponential ones. Even though we're going at this by different methods, the same thing should happen. We got two solutions because we had a second order equation. So moreover, with the second order equation, we have to have two solutions. Our general solution needs to have two linearly independent solutions. So if we have a second order equation, we need to find two linearly independent solutions. I haven't defined what linearly independent means. If there are only two objects, linear independence means one is not a multiple of the other. If there are more than two, then we think of linear independence as one of the elements is not a linear combination of the others. But let's start with just two. For two things, linear independence just means one is not a multiple of the other. Constant multiple of the other. So we take our two solutions and we want to put them into one general solution. Any questions? Okay. We can check to see that this is going to work in our equation. If y is c1 e to the negative t plus c2 e to the 4t, then y prime will be minus c1 e to the negative t plus 4c2 e to the 4t, and y double prime will be positive c1 e to the negative t plus 16 c2 e to the 4t. We should be able to plug these back into the original equation and see that it all cancels out. So here we are plugging in y, y prime, and y double prime to check. Now we have two kinds of terms here. We have your e to the negative t terms and e to the 4t terms. Here I have 1c1e to the negative t minus 3, plus 3 minus 4. So those cancel out. Then I have 16 minus 12 minus another 4. So this all works out to 0. Well, 5 counter-like terms, everything cancels. Questions? Here's the case where we have distinct real zero. Okay. Try not to have waiter style timing, where everybody's still writing stuff down, thinking about it, but while you're in the middle of it, like turn the page. It's like the waiter's like waiting in the wings. It's like, we should go check on that table. Ask how the food is. Hold, they have not taken a bite yet. Then as soon as you stuff a big old bite of food in your mouth, hey, how's the food today? They go, move, 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 move. My mom raised me not to talk of a mouthful. But if you ask me a question, when you know I'm going to be engaged in eating, I'm just going to answer you. I'm just kidding. I just nod. I used to nod and get thumbs up like that. I'm worried, hand gestures you just shouldn't make hand gestures anymore. It's like saying anything. It's just become dirty. So someone's going to be offended. So if you like put a thumbs up, people are like, oh, well, fuck you too then. It's like, well, I just mean, it like means something in different places. It's not the same word everywhere else. You know what I mean? Everything gets just connotation attached to it. It's like, we're going to solve some differential equations if you know what I mean. I mean, see, everything just becomes dirty because humans are garbage. All right, so when we have a second order equation, we want to look at the characteristic polynomial, find the zeros of the characteristic polynomial, and that will give us the two solutions. So here, our characteristic polynomial will be k squared minus 4. And so our solutions, plus or minus 2, we've got distinct real solutions. So our general solution is C1 e to the 2t plus C2 e to the negative 2t. Yeah. So remember what's going on is when we're looking at the differential equation, y double prime minus 4y equals 0, we're making a guess. We guess y is equal to some constant times e to the kt. Then we take derivatives and plug in. So y prime is c times ke to the kt, and y double prime is c times k squared e to the kt. I'm just going to plug these into my original. So I'll have c times k squared e to the kt minus 4 times c e to the kt equals 0. Then we want to solve this for k to figure out the values of k. That's the unknown part in our guess. The constant in front, that will come from initial conditions. We got to figure out what the differential equation is telling us about the value of k. If we factor a ce to the kt out, we're left with k squared minus 4. And so there's our characteristic polynomial. So we want to skip all that and know what's going to happen. We should skip the part where we're writing down our guess until we get the hang of it. What we want to do is look at the equation. Once we classify it as linear, homogeneous with constant coefficients, we go directly to the characteristic polynomial. That's the thing that we wanted to do. Look at this. We want to come up with the characteristic polynomial so we can get at the zeros of the characteristic polynomial and build our general solution. This is how we get to the characteristic polynomial. It comes from that guess. This must have the form e to the kt. And then we just have to figure out what values of k the differential equation will tell us. So the values of k are going to be determined by the differential equation, but the values of C1 and C2 will be determined by the initial conditions. Same as with our separable equation. A differential equation defines a family of functions. The initial conditions narrow it down to one member of that family. Questions? In the previous two examples, the characteristic polynomial had distinct real zeros. They were real and they were different numbers. So we got to look at one where that changes. So here, we're going to have a repeated real zero. Our characteristic polynomial will be k squared minus 6k plus 9. And so the solution is k equals, the solutions are k equals 3 and another k equals 3. K equals 3 twice. And this is a k minus 3 squared. A quadratic equation always has two solutions. If it's a square, then we count that zero, that root, that solution twice. Here's where we run into a problem. Leave the space. With a second order equation, we need two linearly independent solutions. But e to the 3t and e to the 3t are not linearly independent. I can't have C1 e to the 3t and C2 e to the 3t. Those aren't linearly independent. I can just add them together. That's not two different things. That's just one thing. Think of linear independence as Lego blocks. Anyone familiar with Legos? They have the tall Lego and then the flat Lego. How many flat Legos does it take to make a tall Lego? You people said that you understood Legos. Are you not engineers? If you don't know this about Legos, you're not going to make it as an engineer. Get some Legos and start learning this stuff. It's 3 flats make it tall. Come on, man. That's it. I'm walking out. I'm just kidding. So it's the 3 flats make it tall. This is really useful for reinforcing your structure. Since if it's based on tall, but you need something sideways, but something small, you can just like take a little freer and put a flat 3 and then a flat 3 on top, and then a flat 3 sticking out the side with 2 little oneers to make a little joist so you could put little shelves in your Lego bricks. You know what I'm talking about? I don't believe you when you say you know what I'm talking about. You didn't know it was 3 to 1. But anyway, the point is, I'm just kidding. Jeez. Just to act, people. One of these days I'm going to do that, and someone's actually going to get mad. They're going to stand up. They're going, "Fuck you! I'm a Lego expert," and then they'll bring out like certifications and shit. That's all I'm saying. The point is that those tall Legos and the flat Legos are not linearly independent because the tall Lego is a linear combination of the flat ones. I don't really need the tall ones. I can always make a tall one out of 3 flat ones. know what I mean? Linear independence has to do with what we need. What are the building blocks? The periodic table of elements. I'm so glad that I have a classroom with a pretty periodic table. These are your Lego blocks. These are linearly independent. Water is a linear combination of the elements, 2 hydrogen and 1 oxygen. So we don't need a space for water on the periodic table. That would not be linearly independent. If I put water on the periodic table, then the table would not be linearly independent because one of the elements one of the compounds is a linear combination of the others. E to the 3t, even if I have different numbers, C1 and C2, 5e to the 3t plus 7e to the 3t, that's just 12e to the 3t. They're not linearly independent. Any questions? I'm saying this because some of you are going to be taking linear algebra after this class. And that's linear independence. That's how I think of linear independence, the Lego theory of linear independence. The problem is, for reasons, when we have a second order equation, we need 2 linearly independent solutions. Right now we have 1. So we have to do something very sneaky, very complicated, very technical. There, we've done it. There's no trick to it, it's just a simple trick. I haven't said why we definitely need 2. I just told you that we need 2, and right now everybody's going to believe. So here's our general solution when we have repeated real zeros. We should verify that this is in fact a solution to our original differential equation. So I'll take the derivative of the first times the second plus the first times the derivative of the second. I should have factored out the 3t first. What was I thinking? Oh, easy answer. I wasn't. I should have factored out the 3t e to the 3t. I need our second derivative. I'll take the derivative of the first times the second plus the first times the derivative of the second. That's constant. That's constant. The derivative of 3c2t is 3c2. So we got 9c1. Why am I putting that in? I don't know. Plus 3c2 plus 3c2t plus 3c2. So there's plus 6c2 plus 3c2. Why didn't I just leave the 3 out? I don't know why I didn't leave the 3 out. Now I've got y prime, and y double prime. I can plug them back into my original equation. think I messed something up somewhere. 9C1, 9C1, 8 dots 18C1 minus 18C1. So we're good. Any questions? The point, all this stuff has to cancel out. So I've got 9C1 minus 18C1 plus 9C1. So that's all out. I've also got these C2s. So I got 6C2 minus 6C2. Nothing there. And on this, the third one, oh, I ran out of different color. I've got 3C2T minus 18, minus 18. So now I'm off. Minus 18 C2T plus 9. Oh, this one is a 9. Okay, now it's questions? How's everybody okay? Talking about because I started questioning why I was leaving the 3 in or why I was putting the 3 back. So while I was saying, why am I putting the 3 back? I didn't put the 3 back right here. Okay. Now I know what I did and I know why I did it. So it's like when I lose something in the house that I know is supposed to, that I don't really need, but I know it, I don't know where it is. I can't find it. So I like a pen or not like an emergency thing, like I need the keys now. It's just like, oh man, I had that thing. I know it's around here somewhere. I just can't remember where I put it. The most important, and I'll just sit there and I will obsess about it. And I will take the house apart down to the nails until it turns up. And the problem is I can't call for help because my wife is the same way. And so if I can't find something, the worst thing that I could do, so hey, Kat, can you see my AirPods? Because now we're both going to spend the next 2 hours tearing the fucking house apart, trying to find them. And we will not let it go. So when one of us is looking for something, we don't say anything. Unless it's an emergency. Because we're trying to leave and we need our keys. But the keys always go in the box, so. You know what I mean? It's not even that I needed the AirPods. I just happened to notice that I don't know where they are. Because I put them down somewhere stupid. Or worse, I put them in a place that I thought would be really clever. This will be a clever place to keep this item. I'll be able to find it easily. Until I out clever myself. Then I'm looking for it. Kathleen will be like, oh, what you looking for? Nothing. Nothing. So there it is. Questions? Comments? Deep thoughts? I didn't explain why we need 2 linearly independent solutions just because we had a second order equation. And if you're thinking, do we need 3 linearly independent solutions if it's a third order equation? Then the answer is yeah. And we can do the same thing. If I get 3 copies of e to the 3t, I'll put a t on one of them, and then just do that again. So I have a t, c1 e to the 3t, c2 t e to the 3t, and then c3 t squared e to the 3t. Any questions? When I do what? A different function? A different function wouldn't fit the description, right? If we guess sine of t, derivative of sine is cosine, so this would be cosine, and then the second derivative will be back to the negative sign. So the y double prime and the y would have a chance to cancel out, but this y prime, that would have a cosine if we guessed cosine. Hold on to that guess though. What have I done here? I told you at the beginning what I was going to be doing today. What have I done? What's come up? What's our characteristic polynomial? This is the simplest case of the third thing that can happen when we get a quadratic equation. We're going to have complex conjugates as solutions. Well, what are we going to write? E to the IT? That's ridiculous. Oh, hang on. What the heck? There. Let's try this. Let's go back to the equation and see what's supposed to happen. We've got a function and its second derivative. We've got a function and its second derivative, and they need to cancel out. We need a function We need a function where the second derivative is the opposite. And so sine of t fits that bill on what we were just talking about. If y is sine of t, then y prime is cosine of t. That's okay. We don't have any y primes in the equation. And y double prime is negative sine of t. So when I plug these into my original, I get minus sine t plus sine of t equals 0. So that one checks out. So our observation changed a little bit. I didn't like writing this e to the it or e to the minus it. So we went back to look for another guess. We noticed that we need the second derivative and the function to cancel each other out. And sine of t does that. What else does that? What other function will fit this bill? Any other function will fit this bill? If y is cosine t, then y prime is minus sine of t, and y double prime will be minus cosine of t. Plug that into the original differential equation. Minus cosine of t plus cosine of t equals 0. This is good news because we had a second order equation, which means we need to have two linearly independent solutions to the differential equation. And there they are, sine of t and cosine of t. So now we can see what our general solution looks like. C1 sine of t plus C2 cosine of t. Any questions? Incorrect. There is a big question right in front of us. What does cosine of t plus sine of t have to do with e to the it? So that's what we're going to have to deal with. Euler. Here's Euler again. If you've only ever read math, this is how you spell it. Lots of times this comes up, people read this as Euler, which is good. That means you're reading. But not from German. Euler. I can't remember what it's called. He did so much math, he's from everywhere. He belongs to the board. All right. So the k, the two values of k come from the characteristic polynomial. There's zeros of a quadratic polynomial. So we have three things that could happen: distinct real zeros, repeated real zero, complex conjugate zeros. And we've seen how to build the general solution in some of those cases. Here we had solutions that were pure imaginary. What if our solutions are 2 plus or minus 3i or something just actually complex? All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day and thanks for playing.